The next one, somewhat non-trivial, the negative binomial PMF. Which number should I use here? 5? For this I am going to make sure that I say it correctly. So what is this negative binomial PMF? Have you seen this? Is the number correct, 5, or is it should I put something else? I think it's okay. This says, right, repeated trials until kth success, where k is typically larger than 1. Not if you set k equal to 1, then you are back to geometric. Now I am looking for repeated trials until the second success or the third success or whatever, right. Again, the probability on each success is p. Small p. So what happens to omega x, right? The range space. So what will be, what is x first of all? X is number of trials required, right? That is a random variable, x. So what is omega x? You need at least k trials, right, to get k success. So it has to start from k. Right? It cannot. Maybe should I use k or not? Let me not. Again, I may need k. K now becomes a fixed parameter. It's no longer the free variable of the PMF. So maybe we'll make a small change. I wasn't so that I'll be uniform here, right? So this k is not the same as this. So I don't let me use rth here. I'm sorry about this, but I need to change this. Let me put rth success. R is now an integer, right? Please make this small change, right? So omega x in terms of r is what? R starts from r onwards. But you can get r plus 1, r plus 2 like that, right? Any of these are possible. So what is the probability that you get exactly, you need exactly k success where k is one of these integers? How do you write px of k? I am talking of k r successes in k trials, right, where k is at least r obviously, but in general I want an expression, right. Again, combinatorics will be needed here. So what we are saying is, for example, if you want r successes, the last one has to be a success because you are going to stop counting at a success. So how many successes do you need before that? You need k minus 1, sorry, r minus 1 successes you need before the rth success. And how many spots do you have? You have k minus 1 trials for the r minus 1 successes. So therefore there is a combinatorial term here which is basically r minus 1 choose, or sorry, it is k minus 1 choose r minus 1. And you have a sequence of successes and failures. How many successes you have, how many failures you have? You have exactly the r successes and you have k minus r failures. So what will come here? You have, how many successes do you have? We have exactly r successes, right, because that is what we want. You have exactly r successes, right, and therefore k minus r failures. So what, again you should, this by itself is not complete. You should say k greater than or equal to r, right, and it's understood that k is an integer, right, which means to say k equal to r plus 1 and so on. So this is the generalization of geometric PMF. And to show that in general this adds to unity is not that simple, you can go try it at home. I will just do hint at what you have to do for k equal to 2, right. How do you go at it for k? What is the next value? For 1 we have already seen, for r equal to 2. For r equal to 1 you have geometric. What happens when you set r equal to 1? You have to get back. So what, right, you have to get the geometric PMF has what, r equal to 1. What happens if you set r equal to 1 out here? This is always 1, right. K minus 1 choose 0 is always 1 no matter what k you take, and you will get exactly p to the power of 1 minus p to the power of k minus 1, which is exactly what we wrote for the geometric case, isn't it? So this is a generalization. What do you get for k equal to 2, for example? You can obviously, or sorry, r equal to 2, you can always this will be k minus 1 choose 1. So note that this, right, this fact, this is the same for all, I am sorry, no, it's not the same for all k, right. So it's k, what is k minus 1 choose 1? It is basically k minus 1 itself, right. So let me look at it here. R equal to 2 gives you Px of k is what? K minus 1 choose 1 is exactly k minus 1, and you have p power r 1 minus p, so p squared 1 minus p to the power of k minus 2. Now this is somewhat easy to add up, right. Because this p squared does not depend on k. So what tools would you use to add up this sequence? What is the tool you would use? It's a geometry, it's related to, I hope you have seen this kind of a sequence, at least in your DSP class is the latest time you have seen it. You have the terms of the sequence being a product of an arithmetic and geometric progression, right. It is a very, again, very important type of sequence which arises a lot in analytical studies. So this, right, the result is basically this sigma, let me write it down here so I do not mess it up, this m plus 1, you remember this, m plus 1 some q power m from m equal to 0 to infinity. What is this? This is 1 by 1 minus q whole squared. This is another result which I expect you to remember. That is why I am writing it. Of course, this q is between 0 and 1, that I do not have to say that, right. So, so this q is basically this 1 minus p, and you can manipulate this summation to come in this form. Even though you are going to be summing only from r equal to 2 to infinity, or sorry, k equal to 2 to infinity, you can always manipulate it to get it into that form and use that. You can show that easily for k equal to 2. And then maybe you can use induction if you want to show it for any arbitrary r after that, right. So I think I do not want to get any more into this, right, then I leave it at this, right. But this formula again is, I consider it fairly basic, and I think it is fair game to expect you to know it. Even if you can't exactly remember it, you should be able to reason it out. Is this everybody in this class should be able to reason out this, right. Once again, right, you have exactly k r successes in k trials, you have this p power r k minus r, 1 minus p power k minus r, the last one is a success, you have r minus 1 successes in k minus 1 trials, so you have this, you can choose that, you can choose these locations in this many ways. So that is just like the binomial, you get a binomial type coefficient out here. Without this it will not work clearly, right, because these r minus 1 successes can come anywhere in the first k minus 1 trials. You can get them all in the beginning, and then you can get a string of failures, then you can get the kth success, right, sorry, rth success. Okay, so I think let us move on. Again, this is a interesting PMF in many ways, so we should keep this also in our list, right, and Okay. So next, and let me just conclude this list of PMFs by looking at, in a way, something which could have been said earlier, but I am saying it now, the discrete uniform PMF, which we have sort of used implicitly in our die throwing experiments, right? Die tossing. So, and end this series on a very simple, on a simple note, right? So here omega x is very simple, it is just 1 to n, right? N is finite now, right? N cannot be infinity in this case. What is Px of k? The uniform, the term uniform tells you that Px of k is exactly 1 by n for all k. Let me say k equal to 1, 2 up to n. N has to be finite, right? This model cannot be applied to any situation where n grows without bound, right? So this, I said just now, is a generalization of die tossing to any situation where you have a bunch of equally likely outcomes, right? And you can just, all we are saying is we are putting numbers on those outcomes from 1 to n. So if you have equally likely outcomes, you can immediately map it to a uniform, discrete uniform PMF. This should not be confused with the continuous uniform PMF that we will study later on, right? The two are distinctly and totally different, right? They have some commonalities, especially the title is the same, but this, that's why the term discrete is very important here. This is where our knowledge of conditional probability is going to be very helpful. So there is no reason why, right, you can't ask for, given that for example you did not see a success in the first n trials, what is, right, they are going to be the PMF of number of tries needed for success. There is a memoryless property as far as geometric PMF is concerned, but in general, right, supposing you know that the random variable x, something about, so you know some information about it, like it's at least 5 or at least some number m, right, or it's between 1 and 10 or something, right? What can you say about the distribution of x given that x has lies in some interval? That is the most common form in which we see this conditional PMF, right? So maybe I will take it up more in a more detailed fashion tomorrow. I just want to introduce a point now, right? So let us say we condition on the event a less than x less than b. So this x is our random variable, right, and which this includes, for example, a less than x less than b, or I mean could even be equal, or for example x greater than c, or x, well let me just say x greater than b, something like this, right? It obviously the conditioning event has to be very clearly, let me put a here not b, because this is, these two things are pretty much the same if you say b is unbounded, right? So I should use a only to make these two sort of look the same. So now this is an event, hopefully, right, that you have chosen the numbers a and b such that that event has non-zero probability, it has positive probability. You can say given this, that the fact, right, that this has happened, or this is where x lies, right, in a particular experiment, what can you say, what can we say about the probabilities that x is some number k, right, or some value xk, not just k, we have to look at xk, right. So I think instead of looking at the general case, right, what we will do tomorrow is to start this discussion again, right. We will restrict ourselves to the case that omega x is some subset of integers, right, rather than looking at some arbitrary xi, okay. And then we will give some, put some flesh on this point, right. The most important case is the geometry case, right, where you know, for example, what is the meaning of x greater than m, for example, in the geometry case. It means that there has been no success in the first m trials. You had a string of m failures, mf's. What is the probability that the m plus 1 is going to be a success? That kind of, or for the same thing with the Poisson, right. So these kinds of questions are what we are going to answer, we are going to look at tomorrow, right. Okay. So we will stop here today.